What if one of the smallest worlds in our solar system just exposed a climate secret so strange that scientists once thought it sounded crazy? Because when the James Webb Space Telescope looked at Pluto, it did not just see a distant frozen dwarf planet. It found evidence that Pluto's own haze is acting like a planet-sized cooling system, quietly bleeding heat into space. If you love space stories that make the universe feel bigger and weirder with every minute, hit like, subscribe, and share this video with one person who still thinks Pluto is just a tiny icy leftover. For years, Pluto had a problem. Not a little problem. Not the kind of problem you fix by checking one instrument or correcting one number. It had the kind of problem that tells scientists something deep in the model is missing. Pluto's upper atmosphere was too cold, about 30 degrees Celsius colder than it should have been. That gap may not sound dramatic at first, especially when we are already talking about a world so cold that the average temperature is about minus 232 degrees Celsius. But in planetary science, a mismatch like that is a red flag. It means nature is doing something your equations did not fully capture. It means the world out there is not behaving the way you expected. And when that world is Pluto, sitting far out in the Kuiper Belt, more than 3.7 billion miles from the sun on average, the mystery gets even more interesting. Pluto is not supposed to be this complicated. For a long time, people thought of it as a small frozen body at the edge of the solar system. A faint point of light, a relic, a place that might be interesting historically, maybe emotionally, but not necessarily scientifically shocking. Then New Horizons arrived. Be interesting historically, maybe emotionally, but not necessarily scientifically shocking. Then New Horizons arrived in 2015 and changed that picture forever. That flyby was historic for a reason. It was the first spacecraft ever to explore Pluto up close, and it is still the only one. New Horizons revealed mountains, valleys, plains, and glaciers. It showed a world with active geology, nitrogen and methane ice, and a thin atmosphere filled with nitrogen, methane, and carbon monoxide. And hanging in that atmosphere was something beautiful and baffling at the same time, a broad haze. That haze was not just decoration. It was not just something pretty for images. It became the center of one of the strangest climate puzzles in the solar system. After the 2015 flyby, scientists worked to understand Pluto's atmosphere in more detail. They already knew Pluto had a thin, changing atmosphere that expands when it moves closer to the sun and collapses as it moves farther away. They knew sunlight can drive chemistry high above the surface. They knew methane and nitrogen can react under ultraviolet radiation to create complex particles, but they still could not explain why the upper atmosphere was so cold. In 2017, Xi Jiang at the University of California, Santa Cruz proposed a bold answer. He suggested that Pluto's haze particles were not just floating there passively. They were heating up and cooling down in a way that controlled the energy balance of the atmosphere itself. That idea mattered because it went against the normal instinct people have when they think about planetary climate. Usually, when we talk about atmospheres, we think about gases doing the heavy lifting. Carbon dioxide traps heat. Methane absorbs radiation. Pressure, circulation, and chemistry shape temperature. On Pluto, Jiang suggested something different. The haze particles themselves might be driving the climate. He later called it a crazy idea, and you can see why. A small world already famous for being odd might also have an atmosphere regulated by tiny particles, instead of mainly by gas. But what made the idea powerful was not that it sounded dramatic, it was that it made a prediction. If the haze was cooling Pluto, then it should be giving off strong mid-infrared radiation. In simple terms, the haze would absorb energy and then release it outward as heat, letting that energy escape into space. If that was really happening, a powerful enough telescope should be able to detect it. And for a few years, that prediction just sat there, waiting. This is one of the things that makes science so compelling when it works the way it should. A scientist studies a puzzle, forms an explanation, makes a clear prediction, and then has to wait for reality to answer back. Sometimes the answer comes quickly. Sometimes it takes decades. In this case, the answer needed a telescope that had not even launched yet. That telescope was the James Webb Space Telescope. When Webb launched in late 2021, it brought something planetary scientists desperately needed: the power to see faint infrared signals with extraordinary sensitivity. One of its instruments, MIRI, the mid-infrared instrument, was especially important for Pluto. Earlier instruments simply did not have enough sensitivity to open this part of Pluto's spectrum properly. Webb did. And once it did, Pluto stopped being just a beautiful mystery and started becoming a solved one. Researchers used JWST and MIRI to observe the Pluto-Charon system. For the first time, they could separately measure the mid-infrared thermal emission of Pluto and Charon at 15, 18, 21, and 25 micrometers. They also captured a high-quality mid-infrared spectrum of Pluto and its atmosphere from 4.9 to 27 micrometers. That may sound technical, but the meaning is simple. Scientists finally got the kind of data they needed to test whether Pluto's haze was really radiating heat away. And it was. That is the big reveal here. Pluto's haze emits a significant thermal signature. It gives off infrared radiation. It cools the upper atmosphere. According to the observations described by researchers at the Paris Observatory, Pluto's upper atmosphere is about minus 203 degrees Celsius because of the haze, whereas it would be about minus 173 degrees Celsius without it. That is the 30-degree gap. The missing explanation was not hidden underground, not caused by a giant internal engine, not evidence of something artificial. It was the haze. Tiny particles. Huge effect. That is the kind of sentence that sounds simple until you sit with it. A world 39 times farther from the sun than Earth, a world many people still think of as a footnote, turns out to have a climate system so unusual that solid particles appear to control a major part of its atmospheric temperature. That is not normal. In fact, researchers described Pluto's atmosphere as completely different from any other atmosphere in our solar system. And that phrase matters. Completely different. Think about what that means. We have studied Earth, Mars, Venus, Jupiter, Saturn, Titan, Neptune, and many more worlds. We have seen thick atmospheres, thin atmospheres, runaway greenhouse heating, giant storms, methane cycles, dust effects, and layers of haze. Yet Pluto still managed to reveal a new climate mechanism worth calling unique. This is why space science can be so humbling. Every time we think the broad rules are settled, one remote object raises its hand and says, "Not so fast." But to really feel the importance of this, we need to understand what the haze probably is and how it forms. Pluto's atmosphere contains nitrogen, methane, and carbon monoxide. High in that atmosphere, sunlight drives chemistry. Ultraviolet radiation interacts with nitrogen and methane, and those reactions help create tiny hydrocarbon particles. Researchers say these particles are only a few tens of nanometers across at first. As they descend through the atmosphere, they can clump together into larger aggregates and eventually settle toward the surface. So the haze is not random dust. It is the visible result of active chemistry happening over time. It is a product of sunlight, molecules, temperature, and gravity all working together in an extreme environment. And now we know that while those particles are drifting and growing, they are also shaping the thermal balance of the entire atmosphere. That alone would make Pluto fascinating. But the story gets even stranger when Charon enters the picture. Pluto's largest moon, Charon, is enormous relative to Pluto itself. NASA notes that Pluto has 5 known moons, but Charon is by far the biggest, about half Pluto's size. The pair is so unusual that they are often described as a double planet. Charon does not have a significant atmosphere. Like Pluto, its surface is dominated mainly by water ice mixed with ammonia-based compounds. And yet, Charon is not separate from Pluto's atmospheric story. It is part of it. Researchers say methane molecules escaping from Pluto's atmosphere can drift through space and end up on Charon's poles. There, those molecules can be chemically transformed, helping create the dark reddish material seen in Charon's polar regions. In other words, Pluto is not just managing its own climate, it is also feeding material to its moon. Pause on that image for a second. A small dwarf planet with a thin atmosphere is losing methane into space, and some of it settles onto a companion world where chemistry changes the moon's appearance over time. That is not a static system. That is not a dead system. That is a relationship. If this cosmic detective story is pulling you in, press like, subscribe, and send this video to a friend who loves the moment when one weird clue suddenly makes the whole mystery click. And that relationship tells us something important about how wrong first impressions can be. Pluto was discovered in 1930 by Clyde Tombaugh. For decades, it was little more than a distant point of light. Then in 2006, it was reclassified as a dwarf planet by the International Astronomical Union. Publicly, that decision became a cultural event. People argued. People joked. People took sides. But the universe did not care what label we gave Pluto. It kept being whatever it was. And what it was, apparently, was one of the most creatively structured little worlds we have ever studied. This is why the Pluto story feels bigger than Pluto. It is about how science matures. First, you detect an object, then you measure its orbit. Then you classify it. Then you send a mission. Then the mission surprises you. Then a new telescope comes along and reveals that even your surprise was still incomplete. That is what happened here. New Horizons showed Pluto's haze. Zhang proposed that the haze controlled the temperature. Webb then confirmed that prediction by detecting the infrared signature of the haze itself. That clean chain from observation to hypothesis to confirmation is one of the most satisfying things in science. It is not flashy in the way people often imagine discovery. There is no giant explosion, no alien artifact, no instant answer, just a patient buildup of evidence until a hidden mechanism becomes visible. The timeline also gives the story emotional weight. New Horizons flew by Pluto in July 2015. Zhang published the haze idea in 2017. Webb launched in 2021. The new observations in 2023 opened a fresh view into Pluto's atmosphere. And the Nature Astronomy paper, published on June 2, 2025, confirmed the cooling role of the haze. Less than a decade from close flyby to confirmed climate mechanism. In planetaries, science that is impressively fast. And yet the discovery feels almost poetic. Why? Because the answer was floating in the sky the whole time. Pluto's haze had been seen. It had even been admired. But seeing something and understanding what it is doing are two very different things. That is one of the deepest lessons in astronomy. The universe is full of things that look beautiful long before they make sense. A blue haze around Pluto can look like a visual detail. In reality, it can be the key to the planet's energy system. Once you know that, Pluto stops feeling like a frozen postcard and starts feeling like a machine. A strange, elegant machine made of sunlight, methane, nitrogen, infrared radiation, ice cycles, and time. That machine operates under conditions so extreme that even Earth-based intuition can fail us. Here on Earth, atmosphere often means air you can imagine, weather you can feel, clouds you can watch. On Pluto, the atmosphere is thin and tenuous. It expands when Pluto gets closer to the sun and collapses as Pluto moves farther away. Surface ices can turn directly into gas and then later freeze back down. Seasons unfold on timescales that are almost hard to emotionally grasp. Because Pluto takes 248 Earth years to go around the sun. That means one Plutonian year is longer than the history of many modern nations. Its climate changes slowly, but not simply. It breathes over centuries. And in that long, cold breathing cycle, haze appears to matter far more than scientists once expected. There is another reason this discovery deserves attention. It may help us understand other worlds too. Zhang pointed to Titan and Triton as important comparisons. Titan, Saturn's large moon, and Triton, Neptune's large moon, both have nitrogen and hydrocarbon atmospheres with haze particles. They are not identical to Pluto. Titan has a much thicker atmosphere and is famous for methane lakes and rivers. Triton is different again. But the underlying chemistry shares enough similarities that Pluto's case forces scientists to rethink the role haze might be playing elsewhere. That is how one discovery spreads. It begins as a local solution to a local mystery. Then it becomes a framework. Then scientists ask, if haze can dominate climate here, where else could that be true? Maybe on Triton, maybe in parts of Titan's atmosphere, maybe on some distant exoplanets with cold, hazy, nitrogen-rich atmospheres we have barely begun to study. And if that still feels too far away to matter, then bring the story closer to home. Zhang also pointed to early Earth. Before oxygen built up in Earth's atmosphere around 2.4 billion years ago, life already existed, but the atmosphere was very different from the one we know today. It was mostly nitrogen, with a lot of hydrocarbon chemistry. That does not mean early Earth was Pluto. It was not. But it does mean Pluto may preserve chemical and atmospheric processes that echo conditions relevant to Earth's distant past. That is one of the most surprising turns in this entire story. A dwarf planet far beyond Neptune may help scientists think more clearly about the ancient Earth. Not because Pluto is alive, not because Pluto is warm, not because Pluto is secretly Earth-like, but because chemistry does not care about our emotional categories. Sometimes the best place to study a process related to home is a place that feels as far from home as possible. If you have made it this far, you are exactly the kind of viewer this channel is for. So subscribe now, drop a like, and share this video as your invitation to anyone who wants real space science without the hype. Now let's talk about why Webb specifically was the telescope that could settle this. Webb is not just a bigger Hubble. It was designed to see the universe in ways earlier telescopes could not. And for Pluto, the key was infrared sensitivity. Earth's atmosphere makes some infrared observations extremely difficult from the ground. Older space telescopes did not have enough sensitivity or resolving power to fully separate what was coming from Pluto and what was coming from Charon in the right wavelengths. Webb could. That matters because Pluto and Charon are close together from our point of view. If their signals blur together, then you cannot cleanly tell what belongs to Pluto's atmosphere and what belongs to Charon's icy surface. According to the researchers, Webb's observations allowed separate measurements of the two bodies in the mid-infrared. That is the breakthrough. Once those signals were teased apart, Pluto's haze emission stood out. In science, discoveries often depend as much on measurement as on imagination. You can have the right idea and still be stuck until technology catches up. That is exactly what happened here. The prediction existed. The mechanism was plausible, but without the instrument, the mystery remained open. And that should make us appreciate something easy to overlook. The James Webb Space Telescope was not just built to look at the early universe or distant galaxies. It is also changing how we understand objects in our own solar system, even Pluto, especially Pluto. There's a certain beauty in that. A telescope famous for seeing deep into cosmic history turns toward a tiny world at the edge of our own system and solves a climate puzzle hidden in a thin blue haze. And what it finds is not spectacle for spectacle's sake. It is a principle, a real physical principle. Haze particles absorb heat and emit infrared radiation into space, cooling the atmosphere. That means Pluto's climate is not just a balance of sunlight and gas. It is a balance shaped by solid and icy particles suspended in the sky. Once you understand that, Pluto no longer looks like a reduced version of a planet. It looks like its own category of wonder. Maybe that is the emotional core of this whole story. Pluto spent years being treated, in the public mind, like a demoted world, less important, less serious, less worthy of attention. But science keeps doing something beautiful with Pluto. It keeps turning that assumption upside down. The smaller you think Pluto is in significance, the more likely it is to embarrass that assumption with new complexity. It has active geology, it has glaciers, it has seasonal ice redistribution, it has a chemically rich atmosphere, it has a major moon that interacts with escaping material, and now it has a confirmed haze-driven cooling system that appears unlike anything else seen elsewhere in the solar system. That is not a minor object behaving in a minor way. It also helps explain why the Pluto-Charon system fascinates scientists so deeply. This is not just about one world in isolation. It is about surface and atmosphere interacting. It is about chemistry and radiation linking sky and ground. It is about one body affecting another body nearby. It is about how even tiny environments can become laboratories for major ideas. And that is where the real scale of the story comes into focus. Pluto is small. The insight is not. Because when scientists improve models of worlds like Pluto, they're not only trying to understand Pluto better, they are also testing how atmospheres work at the edge cases. They are asking what happens when sunlight is weak, temperatures are brutal, chemistry is slow, and haze becomes powerful. Those edge cases matter because nature is full of them. The universe does not arrange itself to fit the comfortable middle. That is why Pluto can teach us something so valuable. Extreme places reveal rules more clearly. They stretch systems until hidden effects become obvious. On Earth, haze can influence climate, but it does so inside a much more crowded and complicated atmosphere. On Pluto, the effect appears sharp enough to stand out. That makes Pluto a cleaner lesson in what these particles can do. And still, even after all this, there's more to learn. Researchers want to continue studying Pluto over time. That matters, because Pluto's atmosphere changes as it moves along its long elliptical orbit. When Pluto is closer to the Sun, more surface ice can sublimate into gas, thickening the atmosphere. As Pluto moves farther away, gases can cool and return to the surface, thinning it out again. If haze plays a central role in cooling, then scientists will want to understand how that role shifts as the atmosphere itself expands and contracts. In other words, Webb did not close the Pluto story. It opened the next chapter. And that next chapter may tell us how stable this climate mechanism really is. Does the haze always dominate in the same way? Does its influence strengthen or weaken with seasonal changes? How does it affect the movement of ices across Pluto's surface over longer timescales? How tightly is Charon linked to these atmospheric escape processes? These are not side questions. They are the living edge of the science. What makes this so satisfying is that the discovery is strong without needing exaggeration. We do not need to turn Pluto into something mystical. The truth is already strange enough. A haze made from atmospheric chemistry cools Pluto's upper atmosphere by roughly 30 degrees Celsius. Methane escaping Pluto can contribute to the reddish chemistry on Charon's poles. A world many people once dismissed as too small and too distant has revealed a climate behavior that researchers describe as completely different from any other atmosphere in the solar system. That is already incredible. And maybe it tells us something about how we should look at the universe more generally. Not every great scientific discovery comes from the biggest object, the brightest object, or the most obvious object. Sometimes the breakthrough waits on the margins. Sometimes it sits in the cold dark for decades until our instruments finally become good enough to hear what it has been saying all along. That is Pluto in this story. Not loud, not obvious, but profound before we close. It is worth returning to the emotional image that started all of this. Think of Pluto out there in the deep cold, wrapped in a layered haze, dim sunlight touching its atmosphere, microscopic particles forming, drifting, clustering, and glowing in infrared as they send energy outward into the black. It is silent, slow, delicate, and yet it is running a planetary climate system unlike any we have confirmed elsewhere. That is the power of modern astronomy. It can take a tiny point of light and reveal an invisible process so specific, so elegant, and so unexpected that it changes how we think about entire classes of worlds. And it can do something else, too. It can restore a sense of seriousness to places that pop culture has flattened into jokes. Pluto is not just the world that got reclassified. It is not just the former ninth planet. It is not just trivia. Pluto is a real laboratory of planetary physics and chemistry. It is a place where active geology, volatile ices, atmospheric escape, and haze-driven cooling all meet. That is a stunning amount of complexity for a world only about 1,477 miles across, which brings us to the deeper lesson. When we call something small, we often mean unimportant. The universe keeps punishing that habit. Small stars can host remarkable planets. Small galaxies can preserve ancient clues. Small particles can reshape whole atmospheres. And small worlds like Pluto can reveal big truths. If this story changed how you see Pluto, show it some love with a like, subscribe for more deep space breakdowns, and share this with someone who needs one good reason to start taking distant worlds seriously. And that is why this discovery matters beyond a single headline. It is a reminder that science becomes most exciting when evidence forces us to upgrade our imagination. Pluto looked simple from far away. The data said otherwise. The haze looked decorative. The measurements showed that it was powerful. A world many people treated as a downgrade turned into a serious case study in climate physics, atmospheric chemistry, and planetary evolution. That is the quiet drama here. Not that Pluto became magical, but that reality turned out to be more inventive than our first assumptions. What seemed like the edge of relevance became the center of a new idea. So what did the James Webb Space Telescope really reveal about Pluto? Not a monster, not a machine, not a fantasy, something better. It revealed that Pluto's atmosphere hides a real, measurable, elegant piece of physics, a haze born from chemistry, acting like a cooling system, controlling temperature in a way scientists had never confirmed anywhere else in the solar system. It revealed that Pluto and Charon are linked by drifting material. It revealed that a distant dwarf planet can still challenge our most basic assumptions about how climates work. And maybe most importantly, it revealed that the edge of the solar system is not where science becomes simple. It is where science becomes strange, patient, and brilliant. Pluto was never just a leftover rock in the dark. It was a question. And thanks to Webb, we finally understand one of its most beautiful answers.